Hey, thanks for joining me. In this video, we're going to take a look at how to solve a compound body problem. So here we have a hand that's exerting 45 newtons on this group of three different objects here, and they are on a frictionless surface. We're going to figure out three things. We want to figure out the acceleration. We want to figure out the force of tension in rope one right here. And we want to figure out the force of tension in rope two. So as always, I want to start with a free body diagram, or actually in this case, I'm going to do three different free body diagrams of our three different objects, A, B, and C. I always tell people, start with the force of gravity. Almost always going to have a force of gravity acting on an object. The other thing I think of then is where are these objects touching something? So this object makes contact with the ground. Actually, all three of them make contact with the ground. And then there are spots where the ropes make contact with these objects. And the reason I do that is every single spot that there's a contact point, there's going to be a force. So for example, where these objects touch the ground, there's going to be a normal force. There's also a possibility of a friction force wherever something touches the ground, but this is a frictionless surface, so we don't need to worry about that. So then on object A, there's a rope that touches object A right there. So that's going to pull forward on it. I could label that a tension force, but when I'm dealing with a compound body, I like to label it this way, that that's a force on A by B. What's the other part of the object that's exerting a force on it? So a force on A by B. If we turn our attention to object B, it has a contact force on the back, and that's really just the force on B by A. And this is why it's helpful to label it that way. Then you can clearly see, oh, hey, that's an action-reaction pair. Those two are going to be equal and opposite to each other. And that'll help us out later mathematically. All right, this force right here on B is a force on B by C. And then here on C, there's a force on C by B. And finally, there's the hand pulling it. And we don't even have to give that a name. We know it's 45 newtons. I'm just going to write 45 there. Okay. The key to finding acceleration in a compound body problem is to group the objects in your mind as if they are one single object, because essentially they are. A, B, and C are all tied together and moving together. And so then when we write our Newton's second law equation, I'm going to write down all of these sideways forces. By the way, I'm ignoring the up and down direction here. Our acceleration is going to be in the x direction, and the x direction is independent of the y direction. So I'm not even going to worry about those up and down forces. But let's write down the sideways. There's a force on A by B, it's positive. There's a force on B by A that's negative. There's a force on B by C that's positive. There's a force on C by B that's negative. And finally, there's that 45 Newton force. Those are all the sideways forces in our picture. And since we're dealing with all the forces on all the objects, we have to deal with all of the masses of all the objects as well. So that's our Newton's second law equation. Let's put numbers on it now. So, before we do that, the great thing about a compound body problem is the cancellations that occur. And that's why it's nice to write it that way as an action-reaction pair, force on A by B, force on B by A. And because then you really know that those two forces, according to Newton's third law, are exactly the same magnitude. And of course, they point in the opposite direction. And I'll just pause here for a moment and mention that these forces that cancel out are called internal forces. When you look at this red box that I drew, they're all inside of that red box. They're forces that the parts of our object exert on each other. And they're totally within this object. Internal forces always cancel out. And in fact, on tests and quizzes, I won't even require that you write these down here. You just really need to write down the 45 as long as you recognize that these forces cancel each other out. So the 45 newtons, that's called an external force because it's being exerted by an object that is not part of our grouping, part of our system. A, B, and C are part of our system, are part of our grouping. And the hand is not part of that. So the hand exerts an external force. Therefore, it doesn't cancel out when we're just looking at A, B, and C. And only external forces affect the acceleration of an object. So ultimately, when we do our calculation, we're going to have 45 divided by these masses added together, 10 plus 5 plus 15, and that's going to give us 1.5 meters per second squared. That's our answer for acceleration. So now let's figure out this tension right here between A and B. So that's really just the force on A by B or the force on B by A. It doesn't matter which one we calculate. Now, the key to figuring out these internal forces that canceled out of this equation, we can't calculate it from this equation because it canceled out in this equation. We have to regroup this situation. And now I'm going to look at just A all by itself. Just look at A all by itself. And when I do that, here's what my Newton's second law equation would look like. I'm just adding up the forces on A. So that's the force on A by B. And I'm just going to have the mass of A. When I put numbers in that, I know the acceleration is 1.5. And I know the mass of A is 10. And so that means that the force on A by B is 15 newtons. And there's our answer. That's tension 1. That's what I labeled tension 1 in that diagram. So now let's go and try to figure out tension 2, which is really the force between B and C. So I can figure out either the force on B by C or the force on C by B. And again, in order to do that, I have to group things in such a way that the force that I'm trying to figure out, I'm going to try to figure out the force on B by C. I need that to be an external force. So if I just make a box around B and I only think about B, then this is coming from outside of B. Let's look at what that equation would look like. So acceleration is equal to, again, looking at that free body diagram, there's a force, a positive force on B by C and a negative force on B by A. And then we're just looking at B, so I would divide by the mass of B. When I put in the numbers, A is 1.5. The positive force on B by C is what I'm looking for. Now, minus the force on B by A, same magnitude as the force on A by B, 15, divided by the mass of B, which is 5. And when you work out the math on that one, you're going to get that the force on B by C is equal to 22.5 newtons. So you can solve it that way. I want to show you one other way to solve that because maybe you'll like it better. So I chose to group that so that I was only looking at B. But if I want to, I could look at A and B together. So I could group it like this. So you'll notice that the force on B by C that we're looking for is still an external force, but now the force on A by B and the force on B by A, those are internal forces. So I don't even need to know what they are in order to answer this question. So again, if I group these two together, let's see what that ends up looking like in my Newton's second law equation. So I have the force on A by B in there, positive, minus the force on B by A, plus the force on B by C. And then I'm looking at two masses here, the mass of A and the mass of B. These are the forces on both of those masses. Of course, these forces cancel out. And that's what I was saying. We don't even need to know. Let's say we hadn't calculated that up here. Well, we don't need to know what it is because it cancels out. And now we can get an answer to this question by just putting in the force on B by C. Over here, I could have put in the acceleration, should have done that, 1.5, and divide by those two masses added together. So that's going to be 10 plus 5 added together. And so my answer in that situation is, again, going to be 22.5 newtons. So I just wanted to show you an alternate method of solving that problem. And before we leave this video, let me just show you what would happen if, instead of these objects being tied together, what if they're all just touching each other? So same three objects, 10 kilograms, 5 kilograms, 15 kilograms. But now, where's the external force here? Let's say there's a hand back here. Not a great hand. Let's say there's a hand back there that's pushing this way with that 45 Newton force. What would the free body diagram look like in that situation? Maybe, if you want, turn off the video for a moment. And this is still A, this is still B, this is still C. we're going to draw a free body diagram of A, B, and C. But maybe turn off the video for a moment, try to do it on your own, and then turn it back on and see whether your answer matches my answer. Okay, if you're back, let's take a look at A. A's, you know what? I want to follow my own advice and highlight the contact points. So there are contact points with the ground. There are contact points between them where they touch each other. And then the hand is touching A right here. And I'm going to skip the up and down forces. So I'm not going to worry about the contact with the ground that produces a normal force. But looking at object A, right here, it's being touched by the hand. So the hand, this is the 45 Newton force right here. But object A right here is also being touched by object B. And so there's a force on A by B that's backwards. And again, why is this? This is the force in between these two exists because they have electrons on the outside of their surfaces, and those electrons repel each other. So that repulsion is backward on A. If we look at B, right in here where A and B contact each other, that produces a force on B by A. And again, it's really a normal force as the electrons of A repel the electrons of B forward. Then likewise, there's contact right here. Trying to get rid of that screen that just popped up. There we go. And that is a force that's on B by C. And then finally, object C, the only contact point on it that's not down here is this one right here. And so there's a force on C by B. So the rest of this would proceed the same way in terms of if you had to find the acceleration or if you had to find those contact forces. But I just wanted to show you the difference between a problem where the objects are being pushed together and the original problem where they were strung together. All right, see you next time.